Year 13, Year 1, Further Pure, Chapter 4, Matrices and their inverses, Lesson 2, the inverse of a 2 by 2 matrix. So we're going to start by introducing the 2 by 2 identity matrix, which we call I. Sometimes people call it I2 as well, with a subscript 2, and it's 1, 0, 0, 1. Now I can also identify the 3 by 3 identity matrix, which is also called I, or sometimes I3, and it's 1, 0, 0, 0, 1, 0, 0, 0, 1. So ones on the diagonal running from top left to bottom right, zeros everywhere else. And you can have identity matrices which are 4 by 4, 5 by 5, etc. But the identity matrix will always be square, which means it must have the same number of rows and columns. Now the identity matrix behaves a little bit like the number 1. So for instance, 5 multiplied by 1 is equal to 5. 1 multiplied by 5 is still equal to 5. And the identity matrix behaves in a similar way. Let's look at an example. So let's take the identity matrix, 2 by 2, and we'll apply it to the matrix 4, 3, negative 2, and 7. Let's see what happens when we do the matrix multiplication, work it out, and see what you get. So we should get 1 times 5 plus 0 times 3, which is 5. 1 times negative 2 plus 0 times 7, negative 2. 0 times 5 plus 1 times 3, 3. 0 multiplied by negative 2, 1 multiplied by 7, 7. So you get the original matrix. Now, what would have happened if we had completed the matrix multiplication in this order? So reverse the order of the matrices. Try doing the matrix multiplication again and see what you get. So we have 5 times 1 plus negative 2 times 0, 5. 5 times 0 plus negative 2 times 1, negative 2. And 3 times 1 plus 7 times 0, 3 times 0, and 7 times 1. So you get the same result. So the identity matrix, it doesn't matter what order you do the matrix multiplication in, we can say that for a matrix A, the identity matrix multiplied by A is equal to A multiplied by the identity matrix, and the result is A. So the identity matrix represents a transformation in which every point in the coordinate plane maps to itself. So effectively, everything is invariant, i.e. does not change, under the identity transformation. So let's imagine we start with a pair of coordinates x, y. And let's suppose we apply a matrix M to this pair of coordinates, which then takes us to an image pair, x dash, y dash. Let's suppose we then apply another matrix, N, and somehow this then takes us to x, y. Back to the beginning. Well, what does that mean? That means that N must somehow have reversed M, i.e. N is the inverse of the matrix M. But let's look at this overall transformation that takes us from here to the same result. Well, what did we just say? If you apply the identity matrix to a pair of coordinates, you will get the same pair of coordinates. If you apply the identity matrix to any matrix, you will get the same matrix. So this tells me that the combination of M, remember M was applied first and then N was applied second, so it's that order, Mn, must be equal to the identity matrix I. But what did we say about the matrix N? We said that the matrix N is equal to the inverse matrix of M. So we know that M minus 1, M, must equal the identity matrix. And of course, this can work in any order. So M minus 1 will also take us to the identity matrix. Now our job is to see whether we can generalize this. Can we find the inverse of a 2 by 2 matrix in a generalized format? So for instance, if we have any matrix, we can find its inverse and then reverse the transformation created by the first matrix. Let's have a look at this. So let M be the matrix A, B, C, D. Now we know that M multiplied by its inverse matrix must give us the identity matrix I. And so what we're going to do is we're going to call M minus 1, the inverse matrix, P, Q, R, S. And our aim is to find this inverse matrix. So what we know is that A, B, C, D multiplied by P, Q, R, S, the inverse, must take us to the identity matrix 1, 0, 0, 1. So let's do the matrix multiplication on the left-hand side. Be careful with your algebra here. There are going to be a lot of letters involved. Now, check if you got it right. I have put each component in brackets in the pink product matrix, and I've also written the terms alphabetically so it makes it easier to recognise when we have similar terms. Now, from here, we can set up a series of simultaneous equations by equating components. For example, we can equate these two components here. So this tells me that AP plus BR is equal to 1. It tells me that AQ plus BS is equal to 0. CP plus DR is equal to 0. And CQ plus DS is equal to 1. Make a note of these simultaneous equations because we're going to need to eliminate variables between them in order to find P, Q, R and S in terms of A, B, C and D. So I'm going to link this equation here, which contains P and R, and this equation here, which also contains P and R. And separately, I'm going to link this equation here, which contains Q and S, with this equation here, also containing Q and S. So you can see the four equations in the top right-hand corner over here. So if I number them 1, 2, 3 and 4, so you know which ones I'm talking about, we're going to consider, first of all, equations 1 and 3. And equation 1 will tell me that P is equal to 1 minus BR over A, and equation 3 will tell me that P is equal to negative dr over C. So what I can now do is equate these two versions of P, which tells me that 1 minus BR over A is equal to negative dr over C. And let's rearrange this. And we're going to find out what R is. So careful with your algebra. This gives me R in terms of A, B, C and D. So I have one of the components of my inverse matrix in terms of the components of my original matrix. And we know from here that P is equal to negative dr over C, so negative d over C multiplied by R, which we've just found. And carefully, we can see here that we can eliminate C, which gives us P equals negative D over the same denominator, BC minus AD. Careful with your A and D, make sure they don't look similar. So we now have P and R in terms of A, B, C and D. Let's do the same for Q and S. I'm now going to do something similar, this time considering equations 2 and 4. So what do they tell me? So equation 2 tells me that Q is equal to negative BS over A, and 4 tells me that Q is equal to 1 minus ds over C. I could have rearranged for S as well, I've just chosen to do it this way. Now, from here, what do I know? I then know that minus BS over A is equal to 1 minus ds over C, and I can now rearrange this to find out what S is in terms of A, B, C and D because we've eliminated anything else. So what does this give me? Let's keep rearranging it carefully. Tells me that S is equal to this. So S is equal to A over AD minus BC. And you might start to notice a pattern in the three values we've found so far. Q is then equal to negative B over A multiplied by S, which we've just found. So substituting this in, we get a cancellation of A here and here, and this leaves us with Q equals negative B over AD minus BC. So we found P, Q, R and S, which are the components of the inverse matrix, in terms of A, B, C and D, the components of the original matrix. What can we do with this information? So let's remind ourselves that M multiplied by its inverse takes us back to the identity matrix. And the matrices A, B, C, D, which was M, and P, Q, R, S, which was M minus 1, multiply together to give us I. But what we have found is we now know the components of this matrix P, Q, R and S in terms of A, B, C and D. So we know that M minus 1 is equal to, and I'm now going to fill in my components P, Q, R and S. And here we have the four components, and you'll notice there's something very similar about each of the denominators. Now, you should recognise something here. Think back to your previous lesson and the determinant. If you're working out the determinant of this matrix A, B, C, D, which I can write as mod A, B, C, D or det A, B, C, D, that would be equal to AD minus BC. Now you can see that here, and you can almost see that here and here if we deal with the negative signs a little bit differently. So what I'm going to do is I'm going to rewrite the top left-hand component as positive D over AD minus BC. So imagine multiplying the numerator and denominator by negative 1 here. And then the pink term I'm going to leave as minus B over AD minus BC. The blue term, bottom left-hand corner, is going to become negative C over AD minus BC. And then the orange term, bottom right-hand corner, is going to stay as it is, A over AD minus BC. So all terms now have the same denominator, and that denominator is equal to the determinant of the original matrix M. So here's what we can do. We can factorise out a factor of 1 over AD minus BC, like this. And then what do we have left in the matrix? Well, top left-hand corner we have a D, and bottom right-hand corner we have an A. Top right-hand corner we have negative B, bottom left-hand corner we have negative C. Let's now compare the matrix M with its inverse matrix M minus 1, carefully. So let's compare the two. Now, the inverse matrix takes the original matrix, and can you see that these two components swap over? So you have a D here and you have an A here, and then these two components are now the negative versions of themselves. And of course we have 1 over the determinant in front of the whole thing. So we can say that M minus 1 is 1 over the determinant of M and then we have these components here and here. And I think we really need to illustrate this with a numerical example. Now, one important thing to notice here is that you would be faced with a massive problem if a matrix had a determinant of 0. It then wouldn't have an inverse. If a matrix has a determinant of 0, we say it is singular and it has no inverse. So only non-singular matrices have an inverse. So make sure you've made a clear note of this. As you can see, when you're finding the inverse, you're dividing by the determinant of the original matrix. If that determinant is 0, that will cause you a problem. So if a matrix has a determinant of 0, we say it is singular and it has no inverse. Only non-singular matrices have an inverse. And of course, by non-singular, we say that the determinant of the matrix is not equal to 0. So let M equal the matrix 2, 4, 1, 5. Now, what's the determinant of M equal to? Well, it's 2 multiplied by 5, take away 4 multiplied by 1, which is equal to 6. And then according to the formula that we have here, the inverse matrix, minus 1, is 1 over the determinant, so 1, 6. We then swap over these two components, so this becomes 5 and this becomes 2, and we then take the negative of these components, negative 4, negative 1. Now, let's test this out. We're going to work out M multiplied by M minus 1. So that's 2, 1, 4, 5 multiplied by 1, 6, which we can just put anywhere. 5 minus 4 minus 1, 2. So I'm going to pull the factor of a sixth out, and we're then going to do the formal matrix multiplication of these components here. So 2 times 5 is 10. Plus 4 times negative 1 gives me a 6, that's a good start. And then 2 times negative 4 is negative 8, plus 4 times 2, which is 8, gives me 0. 1 times 5 plus 5 times negative 1, 0 in the bottom left hand corner. 1 times negative 4 plus 5 times 2 gives me a positive 6. So I have 1/6 of this matrix, which gives me 1, 0, 0, 1, which of course is the identity matrix. Now, if you wanted to, you can try things in the other order again, M minus 1M this time. So that's 1/6, 5 minus 4 minus 1, 2, multiplied by the original matrix M, 2, 4, 1, 5. Let's multiply these together. So again, let's ring off what we need to multiply. So 5 times 2 is 10, plus 4 times negative 1, 6. 5 times 4, 20, minus 4 times 5, 20, gives us 0. Negative 1 times 2 plus 2 times 1 is 0. Negative 1 times 4 plus 2 times 5, 10, gives me 6. And again, we have 1, 0, 0, 1, the identity matrix. So this illustrates our result. Let's look at one further example here. So A is equal to the matrix negative 2, 1, negative 4, 3. Let's remind ourselves of the inverse matrix result over here. So A minus 1, well, we need 1 over the determinant of A. The determinant of A is negative 2 multiplied by 3 minus 4 multiplied by 1, so that becomes a positive 4. So that becomes negative 2. So we have 1 over negative 2, and then let's remember the rule, we want to swap over these two components, so that's 3 and negative 2, and then we need to change the signs of these components, so that's negative 1 and 4. And I'd probably just tidy that up a little bit, negative a half, 3 minus 1, 4, negative 2. Some people prefer not to have the negative out at the front, so they might rewrite that as a half, and then negative 3, negative 4, 1 and 2. Or you could bring the factor of a half inside if you wished for whatever reason. So you'd have negative 1.5, 0.5, negative 2 and 1 as your alternative answer here. So let's have a look at an example of how we can make use of our matrix inverse. So the point P is mapped to the point Q under the matrix transformation A. Find the coordinates of P. So we know that A applied to the coordinates of P, x, y, give us an end result of Q, 3, negative 10. So what we know is that x, y can be found by applying the inverse matrix A to the coordinates negative 3, 10. So how do you find the matrix inverse of A? Well, first job is to find the determinant of A, which is 5 times 1 take away negative 2 multiplied by 3, which gives us an answer of 11. a minus 1 is then equal to 1 over 11. And then let's remember the technique that we've just seen. We want to swap over 1 and 5. And we want to change the signs of these components. So that's negative 3 and 2. And we're going to take that and we're going to apply that to the point 3, negative 10. Let's see what happens when we do that. So let's apply the matrix multiplication. I'll leave 1/11 where it is. So 1 times 3 is 3, plus negative 3 times negative 10 is 33. It's a good sign. 2 times 3 is 6, plus 5 times negative 10, which is negative 50, gives me negative 44 here. So that gives me 3, negative 4. So the point P is the point 3, negative 4. So let's have a look at the product of a matrix and its inverse in a little bit more detail. So I have A multiplied by A minus 1. Now I'm going to bring this part here out to the front of the multiplication just for neatness. But we then have matrix A, B, C, D, and we're multiplying by the inverse matrix, and we need the rest of that, so that's this. And let's start the multiplication with these two over here. So I'm going to keep my 1 over AD minus BC there. Now the orange parts give me A multiplied by D minus B multiplied by C. Let's now do this multiplied by this, which gives me minus AB plus AB. And what do I have left? So this multiplied by this, which gives me CD minus CD. And then to finish it off, I have this multiplied by this, which gives me minus BC plus AD. Now, what do we have? Well, we certainly have a 0 here and a 0 here, which is absolutely correct. And look at the other parts. Can you see they're both equal to AD minus BC? We have zeros here and here. And so this cancels to give us 1, 0, 0, 1 using the factor of 1 over det A at the start, which is the identity matrix. Now I'm not going to do this, but you could try this yourself and you will see that A minus 1 is equal to A minus 1A, so you could try the multiplication with the order of the matrix and its inverse reversed, and you will still get to the identity matrix I. So, very, very important that we know that result there. So we're going to finish off by exploring what happens if we try and find the inverse of a product of matrices. So I'm going to let my product be Mn. Now it's important here that M and N are non-singular. This means that the determinant of M must not be equal to 0, the determinant of N must not be equal to 0, and M minus 1, the inverse of M, and N minus 1, the inverse of N, both exist. This wouldn't work if either of them had a determinant of 0. So, let's imagine we apply Mn, the order being n first and then m, so I suppose it's m as the pre-multiplier here, and let's call x the inverse of this product, so that x as a multiplier of mn results in the identity matrix. So x is the inverse of the product mn. Now, I'm going to do a little bit of rewriting here. Matrix multiplication, when you have a triple product like this, can be written like this. So I could do x multiplied by m and then multiply it by n, or I could do mn and then pre-multiply by x. It doesn't actually matter, both of those will work. Now, what I'm going to do is I'm going to post-multiply, which means include it at the end, by n minus 1. So on the right-hand side, I would have to post-multiply by n minus 1 as well. Remember, that's the inverse of n and it exists. But look here. What happens if we have n minus 1? It's the identity matrix. So on the left-hand side, we now have x, m, I, and on the right-hand side, we have I, n minus 1. But what do we know? The identity matrix multiplied by another matrix doesn't cause any change. So xmi on the left-hand side is simply xm, because multiplying by the identity won't change it. And on the right-hand side, I n minus 1 is simply n minus 1. Again, remember the identity is like multiplying by 1. So now, on both sides, I'm going to post-multiply by m minus 1. So on the left, I've got xm n minus 1, m minus 1, sorry, and on the right-hand side, I've got n minus 1, and remember I'm post-multiplying, so it's m minus 1 here. And what do we have? m minus 1 is the identity. So I have x, I, is equal to n minus 1, m minus 1. And of course, on the left-hand side, the identity makes no difference, so it's just x. So x is equal to n minus 1, m minus 1. But remember, x is the inverse of mn. So what we know is that if we have a product of matrices mn, the inverse of this product is n minus 1, m minus 1. Now, why does that make sense? Well, because if you look at the product mn, and if you apply that to some pair of coordinates x, what's happening is that we are starting with the pair of coordinates, we are applying the matrix n first of all because it's closest, and we're then applying the matrix m. So if we want to reverse that, once we get to the image coordinate, and we want to go backwards, well then, of course, we've got to apply m minus 1 first, and then apply n minus 1 afterwards to take us back to x, y. So it makes perfect sense that m minus 1 has to be applied first, and then n minus 1. And you can see that here, because this is furthest to the right, that means n minus 1 first, and then n minus 1 second in the order of transformations. So the crucial thing that you have to remember here is that the inverse of the product, mn minus 1, is this pair product of matrices here, and the order matters.